Hey everybody. Today we're going to do some truss problems and just a quick little video to help make these concepts click a little better for you is the intent. Okay, let us get going. So this is problem 4 of the truss unit on seeing structures. And it says that we've got a 60 kip external force. There it is right there. And we need to solve internal forces in members 1, 2, and 3. And it kind of gives you some hints about a way to approach this. So we are going to basically do what the instructions said. All right, so the picture at the bottom means that we have kind of broken the truss up into the different nodes, A, B, and C. Each node has to be in nodal equilibrium, particle equilibrium, equilibrium of a point, all those ideas. But I'm going to come up here to the top, and I'm going to take away the support at A and replace it with potential vertical and horizontal reactions. Similarly, I'm going to go to the roller at B and replace it with a potential horizontal reaction. And doing a little qualitative equilibrium on that global free body at the top, goodness, sum of forces in the y direction, I know right off the bat that AY is going to be equal to 60 kips. So with that information, I will update the picture down below as we go. And I have a little shortcut for units. A lot of times I just label the units once, and then that way when I'm doing method of joints, I don't have to write units with every term. Let's do a little more qualitative equilibrium. So if I were to do a qualitative moment equation about B, the truss tends to rotate clockwise due to the 60 kip force. So I need to anchor the top of the truss at A with a tension force, a pull. So we could think about that as like nailing it into the wall or gluing it to the wall or welding it to the wall. We could also do that quantitatively. And so we would say the summation of moments about B is equal to 0. This way is positive. And so we have 60 kips at a distance of 12 feet. And that one is negative. We have a x at a distance of, so we need this dimension here. Okay, so we'll get that in a second. And that one is going to be positive and it's equal to 0. To get that dimension, we just want to look at the ratio that's given as well as this length. So 12 divided by 4 is 3 times 3 gives me 9 feet. That's what goes in the parentheses here. In my calculator, I'll say 60 times 12 divided by 9 equals 80. And that's how I know that AX is equal to 80 kips. Update it up top and update it down below as well. Okay, going back to global equilibrium up top, I need to balance out that 80 kips. So leftward at A means rightward at B, and so I've got 80 kips down here as well. That shows up as my B of X in the diagram down below. Now that I've got my reactions, I can move into the method of joints. And by the way, you don't always have to do things in this order. Sometimes it is necessary, but oftentimes it's not. For example, node C over here only has 2 unknowns, so we completely could have started there. When I do the method of joints, though, I always pick the easiest joint first and then go to the more challenging ones later. So if I look at A, B, and C, B looks really appealing because number 1, there's only 2 unknowns. Excuse me, I had to sneeze. Number 2, everything's at 90 degrees. So goodness, at node B, summation of forces in the y direction equals 0. That means force 1 is a 0 force member. So that's the first thing that we've solved. We can just take it off the board. And if we're going to tabulate our answers over here, the internal force in member number 1 is 0 units of kips if you want to add those in. All right, B, we've got to finish off, and this looks pretty straightforward, except for you probably caught my error before I did. See how that was a push there, and then I turned it into a pull. That was not intentional, just an error. So let's get that fixed. It's a good example of how when you're doing a problem like this with multiple members, you got to stay focused and check your work and go at a good pace for you. All right, back to B. So I've got a push. I need an equal and opposite push, changing over to an orange color for my internal forces. F sub 3 is 80. Node B or joint B is fully solved. So now I'm ready to move to another nodal equilibrium problem. Let's use Newton's third law. So what this 80 vector is, 80 kips, it tells me that member 3 is pushing on B. Therefore, it also pushes on C. If the member is in compression, all it can do is push. So we also have 80 right there. Okay, at this point, we can choose node A or node C. I'm going to go to node C. Either one would have been okay. And I'm looking at the line of action of F2. So vertically, I need an upward force of 60. And horizontally, I need a leftward force of 80. So those two forces are the components of an overall tension force. How do I know it's tension? Well, I'm doing a free body of node C, and those vectors show that member 2 pull on node C arrows away from the body. In this case, the body is C. And we could just do a quick little Pythagorean theorem. Actually, it's a 3, 4, 5 triangle, right? So 60 is to 3, as 80 is to 4, as the force in member 2 is to 100 kips. And it is a pull, and so that one will be in tension. Now, I have a habit, so you could come in here and write 100. While I'm solving the truss, I work in terms of the components. It's an enormous time saver. And then I deal with the resultant force, usually is the last step. All right, to finish off this problem, we can go to node A, and this is a check step. So we want to get in Newton's third law for F2. So F2 is a pull. The pull has a downward component of 60, a rightward component of 80. So now I can spot check that node, and is it in static equilibrium? 60 up and down, 80 left and right. That one is done. Okay, so that is basically all we need to do. We just need to report F sub 3. So F sub 3 is equal to 80 kips. It is a push. A push means compression, and those are your final answers. That was fun. Let's do another. So I'm going to pop over to this problem. And in this problem, this is, I believe, number 5 on the Seeing Structures website, Truss unit. And this one takes the training wheels off a little bit, as you can see. Okay, so we're going to have to do the method of joints ourselves, and we want to fully solve this truss. And the first thing to clue into is that when you have symmetry, use it to your advantage. So I'm going to take my symmetry line right here in the middle, and I'm going to lock it in. I'm going to lock it in right there. And I'm going to make it I'll leave it, no, I'll make it invisible. Okay, so it's locked in, but invisible. And that's going to allow me to do some things like this. My loads are symmetric. At A and C, I have the capability for a vertical reaction force. So I have that. Looking at the context up above, C is a roller. That means no horizontal component at C. By global equilibrium, there means no horizontal component reaction at A. 20 times 3 is 60 divided by 2, and that gives me 30. And these are all in kilonewtons, all kilonewtons units. Okay, and obviously, since I'm doing mirror images, some of the text is going to be backwards, and hopefully that is okay and we can live with it. I still like to use the symmetry as a teaching tool. Okay, we are ready to start working through our method of joints. So we find a joint that looks good to us, and A looks pretty good. So why don't we come over here we're going to detach members 1 and 2 from A and replace them with their effects on the body. So vertically, I need a downward 30. That tells me that the force in member 1 is 30 kilonewtons. And since I don't have anything to balance a potential force horizontally, I know that member 2 is a zero force member. So for the purpose of my analysis, that means I can just pretend that member 2 doesn't exist. And I'll start to tabulate our answers. So far we've determined that the force in member 1 is 30 kilonewtons of compression, and that the force in member 2 is 0. Let's continue on our way. Node A is balanced. So let's, first of all, put Newton's third law into practice. So I want to do a push force at G. So I have 30 there. And let us see. I think the next easiest node, just kind of scanning everything, why don't we go do E? Let's go take a look at E. So vertically at E, I'm going to disconnect it from 5. 5 has to push upwards to counteract the 20. And I'll turn off my line of symmetry just for a second for the label. And if I use Newton's third law, that means that that push also applies to B. Pushing at B with a force of 20 kilonewtons. Now, if I were to go to node E now, I would see that, the force in member 4 is the same on both sides, but I can't solve anything. But if I go to node B, now I'm going to be able to solve things. So let's go down to B, and I'm going to take away, I'm going to kind of hatch this out a little bit so we can sort of see what's going on. Okay, how about that? So I've got to take out a downward force of 20 because it's symmetric. I know I'm going to get 10 on both sides. Because it's symmetric, I know I'm going to get 10 on both sides. So I see that member 3 is in tension, a pull, because I'm working on node B and those arrows are pointing away from the body. Now I want to use the aspect ratio to do the horizontal pull. So I say 10 is to 6 as unknown is to 8. Okay, so in terms of my calculator operation, I would say 10 divided by 6 times 8. Like scale it down, scale it back up. We can get a horizontal of 13.3 bar. Now node B is done. So node B is done. Node A is done. Let's use Newton's third law to put the forces of member 3 on G. So by Newton's third law, right? So I do have a pull. That's clear from here, arrows away from the body. But it's easier to work through a truss in terms of components. So we'll do a pull of 13.3 bar and a pull vertically of 10. All right, let's go on to node G. So G is looking pretty good. I have to remove member 4 and replace it with its effect on node G. So get member 4 out of there and get my orange color for internal forces. Let's spot check vertical equilibrium. So 20 and 10 is equal to 30. That's a good check, right? Because if you made a mistake somewhere and things get out of kilter, you got to backtrack and find your error before going forward. But that's looking good. So I just need to balance out the pull. So I want a push compressive force of 13.3 bar. With that move, my free body up at the corners is done. And lastly, I go to node E and do a little Newton's third law. So let's remove members 4 and take this push of 13.3 and have it also push on E, 13.3 bar. And that one is clearly in equilibrium because of the symmetry. So in terms of like your final answer, you would say F1 is 30 kilonewtons of compression, F2 is equal to 0, F4 is equal to 13.3 bar kilonewtons of compression. That's a push. And let's see, member five has 20 of compression. That's a push. And member three, the inclined member, I've got 10 and 13.3 bar. So what I would probably do is just do 10 squared plus 13.3 squared and take the square root of that and come up with 16.6. That is the tension force in number three. All right, let's do another one. Let's do another one. So here is another problem. Called this one problem 6 in the set. And again, we start with our global equilibrium tools. This one definitely doesn't have symmetry, so no symmetry on this one. In order to be symmetric, it needs to be symmetric both in terms of geometry and forces. And that symmetry is with respect not to the loading diagram, but with respect to the free body. All right, well, let's see. Let's remove the roller at D, and that can only give us a horizontal push or pull. So I'm just going to draw a horizontal line for now, and we'll figure out if it's a push or pull here in a moment. Down at A with my pin support, I'm going to swap that one out with vertical and horizontal components. So I have the potential for a horizontal, I have the potential for a vertical. And at this point, I usually go, I start with global equilibrium because a lot of times you can solve some things pretty quickly there. And I only have one vertical unknown reaction. So it needs to balance out that load. So I can solve right off the bat that A sub Y matches the 10 kip force there. And as before, just kind of all kips. And then I can just work with numbers on my diagram down below. Okay, for the horizontals, we can do a moment summation about one to find the other. So let's try this. Let's do the summation of moments about A and set that equal to 0. So I'm going to have 1, 2, 3 terms in my moment summation. And at this point, I do need to take a stand and decide whether I want D to be a push or a pull. Looking at the loads, my intuition says, let's assume a push. And so we'll call this unknown D sub x. We go into our equation, first term, 10 kips, oops, different pen. Okay, so 10 kips times 10 feet, and that one has a negative tendency to rotate about A. We have second term, 10 kips times 16 feet, and that one also has a negative tendency to rotate about A. Last term, we have dx times 10 feet. Set that equal to 0, and that last term has a positive tendency to rotate about A. So looking at my calculator, first term I have negative 100, and then I want to subtract 160. I want to multiply by negative 1 to get it to the other side of the equal sign and divide by 10. And so dx is equal to 26. The positive sign verifies or confirms the direction that I assumed. So now we know that this is 26 kips. With that in mind, we can now solve for our final unknown reaction. So A sub x is going to have the net force required to balance out these two forces. So 26 less 10 is 16. What direction does it need to go for equilibrium? It needs to go rightward. Now that we have our reactions looking good, we are ready to do our method of joints. And as always, I'm scanning and trying to find the best, easiest place to start. So A has 2 unknowns, C has 3 unknowns, B has 3 unknowns and no numbers, so that one's definitely not a good place to start. But D is attractive because 2 unknowns and one of them is horizontal. That is a win. Now, as we analyze node D, we're going to see that one of these is a zero force member. So think about the logic. In member 4, I only got a horizontal. In the inclined member, any force produces both horizontal and vertical components. Since I don't have anything to balance out a potential vertical component there, that's how I know that member 5 is a zero force member. Member 5 is a zero force member. So for the purpose of our analysis, it's like it's not even there. Just pull it off of the board. At D, looking at that summation of forces in the x direction equals 0, can easily balance that out with a push of 26. 26 kips. Let's use Newton's third law to get that force over to node C. So push of 26 at C. All right. I'm looking at C. C has 2 unknowns, but both funky angles. And A has 2 unknowns, one at a right angle. So at this point in my process, A looks like the best node to go to. So let's go to A and we detach it from member 1. And we detach it from member 2. And every time we detach something, we replace it with its effects on the body. So what is the effect of member 1 on A? Well, it's a force inclined. So it has a vertical and horizontal component. What is the effect of member 2 on A? We have a horizontal force there. All right, so my deductive reasoning is going to go in this way. I've got unknown horizontals for both of those, so I don't want to mess with horizontals. For verticals, all of that vertical force has to go in the inclined member. So I need 10 down to balance out the 10 up. So I'm already seeing push forces. So member 1's going to be in compression, pushing on the node pushes back, compression transferred between 1 and A and 1 and C. Next, I use ratios. 10 is to 10 as a force is to 16. So clearly this one is 16 kips. I'm going to go ahead and make these a little more prominent. Let's see, finishing out and balancing node A. So in the vertical direction, 10 versus 10 balances. In the horizontal direction, 16 versus 16 balances. What does that tell us about member 2? It's actually a zero force member as well. Let's take it off the board. Once we make that deduction, we can run over to joint B. Is there any way to get equilibrium with one force on member B? No way. Therefore, member 3 is also a zero force member. So our actual structure in this problem is just a strut, basically a compressive strut with an angle in it that's going between A and D. Okay, so, and again, we can build whatever we want, but the forces will flow in the way that is most natural to get that load into the supports. All right, I believe we're done with this one. So again, with the method of joints, one reason I like it so much is that I can always come and check my work with the last node. So you cross your fingers, hold your breath, and do this. Newton's third law, so 10 down means 10 up. You can also, well, actually, it's not a Newton's third law thing. It's more like, okay, so the force in member 1 is a push. So I'm going to push here and here. And the result of that is that you flip the direction of the arrows. Right, and that is it. So let us spot check equilibrium. So this node obviously in equilibrium, This node is in equilibrium. What about the one in the middle? So vertically, 10 balances with 10. Done. Horizontally, 26 balances with 26. Done. So in terms of reporting final answer, the force in member 4 is 26 kips of compression. The force in member 1 is 10 squared plus 16 squared, square root of that, to get 18.9 kips of compression. And everything else is a zero force member. Let's do one more. So I'm going to go over to problem 7. And problem 7 has some lovely symmetry. So I'm going to use my symmetry tool again. Let's put it in the right place. Unlock it. There we go. Okay. So we're going to put it in the right place down here. Close enough. And lock it in. And I'm going to hide that. Let us go. So beautiful symmetric truss. Symmetry makes my heart sing. I can remove the support at A and at M. A can do vertical and horizontal. M can do vertical only. My horizontal forces in the system balance out, so I don't have any horizontal reactions. My reactions will be upward and equal to the total load of 120 divided by 2. So 120 kilonewtons on both sides. We are ready to start our method of joints. And again, I'm scanning everything. What is the best place to start? And node E, man, I see something right away. Do you see something at node E? At node E, 7 doesn't have anything to balance it out. So 7 is a zero force member. Get it out of there. All right. Node B and G. 3 doesn't have anything to balance it out at B and G. Therefore, it has to be 0. Get that one off the picture. All right, now that we're down to these source triangles, there's nothing else we can do to simplify, and we're ready to just crunch through the problem. So node D is no good. There's no numbers on it. Node A, 2 unknowns. Node C, 3 unknowns. Clearly, node A is the best choice. Remove member 2. Remove member 1. Replace them with their effects on the body. So I just start out with the lines, as you know. So there is a horizontal force and an inclined force. I need to balance out the 120 vertically. So I'm going to do 120 down here. Looking at my geometry, I've got the 15 and 15. So if this is 120 down, I need 120 rightward. So I've got to pull components of 120. Member 2, therefore, is a push, and that one is equal to 120. That up just a little bit. Okay, let's take that information and bring it over to B and C. So node A is done. At B, so I've got 120. It is a push, so I push with 120 there. And down at C, I have pulls. So I have 120 pull and I have a 120 pull. Let's go over to node B. Nice, easy one to put in static equilibrium. Member 4 must deliver a push to B equal to 120. And then I can bring that over here to D as well. So node B is in equilibrium. Okay, what node looks better? I kind of like D. I kind of like D because of the symmetry. So let's do D. C is also solvable. But we're going to go with D. Here's why. So I'm going to remove member 5 and replace it with that force at 45-degree angles. So to balance this out, oh, actually, I can't do this one yet. I can't do this one yet. Actually, I can. I can, but I'm going to jump over to C. Okay, we're going to come back to that one. All right, let's jump over to C. So at C, we have two unknowns. Pop those in. So an inclined force in member 5, horizontal force in member 6. And what I see is vertically, I'm already balanced, 120 up, 120 down. What that tells me is that member 5 is a zero force member. If it had a force, it would throw this joint out of equilibrium in terms of vertical forces. In the X direction, the horizontal direction, I just need to sum up 100 and 120 to 220 and do that as a pull right there. That would be 220 here. Okay. And now that node is balanced. Now I could have made the same deduction up at D. Do you see that? So at first you're like, well, due to symmetry, this could be a push or a pull. And regardless of that, the horizontals would balance, but there would be a net vertical force. So you could also determine that this is a zero force member from node D. All right, we're almost done. Popping over to E, and all I need to do is remove member 6 and replace it with a pull force in the X direction. All my nodal free bodies are completely done. And so I can finish up this problem by reporting the final answers. Okay, I'll let you do that one on your own. For these inclined ones, right, you would just take 120 squared plus 120 squared, and then the square root of that, or you could take 120 divided by 0.7071, or 120 divided by the square root of 2, all that times the square root of 2. However you want to do it, but you do need to get the resultant forces for your final answers. I hope this video was helpful in demystifying trusses. They're pretty straightforward and kind of fun once you get the hang of how they work. Have a great day.